Now let's do a forces review. Suppose I have two sets of oil drops. I have a car and it's leaking oil. And I want to see what does my free body diagram look like for both of these oil drops. Remember, from an oil drop, you can always tell the direction of the acceleration. The acceleration always points in the direction of the larger dots. So for the top one, my acceleration points to the right. So here's my car. It has some mass m. It has some weight, Fg. It has a normal force. And because the acceleration is to the right, that means the applied force must also be to the right. Now for the lower oil drop, the acceleration is pointing to the left because the dots are further apart to the left. So you have Fg going down, Fn going up, and in this case your applied force is to the left. In both of these cases, we're not putting another force going in the opposite direction, although there could be other forces. And this would just be the net force. Now suppose we have a problem where I have a 10 kilogram block, this is my mass, with a coefficient of friction of 0.1, mu. Find Fg. I'm going to write my givens over here. M is 10 kilograms, and mu is 0.01. Now Fg is always the weight. And you remember the formula, Fg equals mg. So Fg is m, which is 10, times g, which is 9.8, or 98 newtons. To find Fn, you have to go to the free body diagram. We haven't drawn it yet. So let's see. I have a box. Fg goes down, and Fn points up. Now I have a coefficient of friction. Down here I see I'm looking for static, so I'm pretty sure this is static friction. So I'm just going to pretend like we have a force and an Fs. Now for the free body diagram, I need to sum the forces in y to get the normal force. Now what are the only forces acting in y? Well, they're Fn and Fg. And it is not moving in y. Because it's not moving, that tells us the acceleration is going to be 0. Now, this side of the equation is always the arrows from your free body diagram. So what arrows are we going to put in? Well, Fn points up, Fg points down, and this is equal to 0. To solve for the normal force, we add Fg to both sides, and we add it because when we cover up Fn, we see that we're subtracting Fg. Fg goes away. So Fn is equal to Fg, which is 98 newtons. Now I'm looking for static friction. For this one, we go back to our equation that friction, static, is equal to mu Fn. And this is actually mu static, which means it's not moving just yet. So mu s we're given from the problem, not very clearly, but we were given, it is 0.01. And the normal force is 98. So the frictional force is 0.98 newtons. Suppose in this problem I apply a 100 Newton force and I have an acceleration of 2 meters per second squared. What's my mass? Well, let's use guess on this. The givens are the applied force is 100 newtons. The acceleration is 2 meters per second squared. The unknown, what's my mass? I'm looking for mass. Equation, well, the only equation we have is F equals ma. I'm looking for mass, So I'm going to solve this. So m is equal to, let's see, I'm going to divide both sides through by a so that the a's go away. So m is F divided by a. Now for my solution, the mass is the force, which is 100 newtons, divided by a, which is 2 meters per second squared. And I get this is 50 kilograms. Now how would I grade this? Givens are going to be 2 points. Unknown is a point. Your equation is a point, and solving it's a point. You get a point for plugging in your numbers, a point for the answer in units. So that's 1, 2, 3, 4, 5, 6, 7, 8. 8-point problem. Now let's go through very quickly a series of multiple choice questions. Now some of these will have one answer, some will have multiple answers, some might not have any answers. What is mu? Mu, if I just give you mu, it's a coefficient of friction. It is also the relationship between the frictional force and the normal force for two surfaces. Because you remember, friction is equal to mu Fn. So when I solve this for mu, this is equal to friction divided by the normal force. So it's that relationship between friction and normal. So I guess the really correct answer for this one is E. What is mu K? Now that K right there tells me it's kinetic. Now, you're going to want to say that it's the amount of energy needed to keep the box sliding. We have not even discussed energy yet, so it can't be that one. You might say it's coefficient of friction, but because of that K, that tells me it's a coefficient of kinetic friction. Now this S right here tells me we're dealing with static friction. And it's also the coefficient of friction that tells us how hard we have to push to start it sliding. Now, let's figure out what formula we would use. If this is my free body diagram, let's see. I have no vectors in x, so I'm not going to mess with that one. I'm not going to mess with anything with an x in it. This is a formula for kinetic and static friction. Basically what this is telling me is I'm looking for my net force in y is equal to what? If these arrows are the same length, then I'm looking for the sum of the forces in y is 0. So this is if they're the same length. Okay. And the sum of forces in y equals ma is the one we want if they're different lengths. And I believe these are the same length, so our answer is 1. What formula here? We have an acceleration going down. For the same reasons before, it can't be x. I don't have any arrows acting in x, and that's the definition of friction, kinetic and static. So now I have an acceleration. Well, because I have an acceleration, I know it can't be the sum of the forces is equal to 0. So my answer is 4. Now let's look at this. I've got a velocity going to the right, but I don't have any forces on my free body diagram. So there are no forces to sum in x. There's no friction. Not seeing that. I've got the situation here. The sum of the forces in y is 0. I don't have an acceleration in y, so it can't be that one. So my answer is 1. Now, this one gets interesting. I have the sum of the forces in y equals 0. So I know I have to use this one. I have a velocity, so I know it's moving to the right. But this right here tells me I have an acceleration in the x. I have an unbalanced force in x. So I know I need this one as well. Because it's moving, if this is a frictional force, I'm going to need Fk is mu k. Now this one, well, it's not moving in x, but this one, it is, we're not sure if it's moving in x, but this one's a lot longer. So I'm going to assume there is an acceleration going to the right. So this one would be the sum of the forces in x equals ma. We're probably dealing with a block sitting on a table, so the sum of the forces in y is 0. We may have friction, who knows. So, yeah, this is probably moving, so maybe Fk is mu k Fn. And we know it's a frictional force because it's, see how I've drawn it, contact, right there at the bottom. What's the weight? Okay, weight is equal to Fg, and Fg is always equal to mg. What's the normal force? Okay, this is going to take a little bit of thinking. If I finish my free body diagram, the normal force must equal Fg, which is mg. Why? Because the net force in y is 0. And the forces I have going up are Fn. The forces I have go down are Fg, and this must equal 0. So the normal force must equal Fg, which is mg. So this one had quite a number of steps to get to the answer. Alright, what happens if I do a quick jerk on a string? Try this at home. I have a link for you to look at later on. If you do a quick jerk on the string, if you pull very, very fast, then the inertia of the ball is going to act like a fixed point, like something very, very massive. So what you will find is that your lower string is going to break, and it's going to break because the ball has inertia. The ball is very large. Now what if you do a very slow pull? Well, if you do a very slow pull, then the force has a chance to go through the ball and up to the ceiling. And so your upper string is going to wind up breaking because of the force of the pull. And here is an interesting YouTube video where they do a physical demonstration. Alright, what's the mass of a 20 Newton box? If I tell you it's something is 20 newtons, this is its weight. Now let's see, Fg is mg, so I'm looking for the mass m. To find the mass m from this, I'm going to divide both sides through by g. So the mass is Fg divided by g. So that's 20 divided by 9.8, or let's see, around 2 kilograms. Slightly over 2.1 kilograms? 2.2. Now what's the weight of a 20 kilogram box? The weight is Fg, and this is the mass. Fg is mg. The mass is 20. G is 9.8. So this is 196 newtons. Which vector correctly represents the weight of a box? You remember the weight of a box always points straight down. Which vector correctly represents the weight of a box on a hill? Now we didn't really do these, but the weight always points straight down. So again, it's B. Which vector correctly represents the normal force? Now remember, in our problems, we're always sitting on a horizontal surface, so the normal force will always point straight up. Why does a tablecloth trick work? That is, why does your glassware always stay in place? Well, let's see. The tablecloth is pulled out, and the glassware has inertia, and the glassware does not want to move. Now, what do we mean by equilibrium? What do I mean when I say two objects are in equilibrium? Pretty much that means the net forces are zero. Another way you can write this is the forces up equal the forces down, and the forces left equal the forces right. The forces are in balance is not correct. If they're unbalanced, you have acceleration. Now, an astronaut throws a hammer at the sun while outside the space station. The hammer will require a force equal to mg to keep it going. No. The hammer will require no force to keep it going. The hammer will travel at the same speed as the astronaut threw it until it melts in the sun's corona. Well, yeah, until it's caught into some sort of gravity well. So this one might be right. The hammer will take energy from the sun's rays and keeps going. No. That's sci-fi. If the astronaut throws a hammer at the sun while outside the space station, how much force is needed to keep it moving? Now, F equals, remember in outer space, it's going to travel at a constant velocity. We're assuming there are no other forces acting. So zero force will be needed to keep it moving once it's already moving. If the gravity of the Earth suddenly stopped, what would happen to the moon? Here's the Earth, and here's the moon. Now the moon is held in orbit because of gravity. If something happened, the moon would shoot straight off the instant gravity stopped. The law of inertia applies to all objects, whether they're moving or at rest. The law of inertia, you remember, is the first law. The action-reaction law is the third law. F equals ma, second law. Let's see, an object at rest will stay at rest unless acted on by an outside force. We know that to be the first law. I push on the wall with a force, and the wall pushes back at me with the same force. That's the third law. You can always tell third laws because there are two objects, and the forces are the same, but opposite directions. An object traveling in a straight line wants to stay traveling in a straight line. That's the law of inertia. It doesn't want to change. An object traveling with constant velocity wants to stay traveling at constant velocity. First law. See how picky we get with these. Alright. This box will accelerate to the right. Which law are we going to use to explain this? Well, that's the second law. F net equals ma. Which force could be friction? Well, friction will always be the smaller force, so it's got to be the left one. I have a box that has a mass of 50 kilograms. You have a box of mass 25. Whose box has more inertia? Well, since mass is a measure of inertia, the more massive box has more inertia. Unbalanced forces cause acceleration. Do you remember who said that? Galileo. The Earth rotates around the sun. Copernicus. Which one said that bodies seek their natural state? Smoke wants to be in the air. Pencil wants to be on the ground. You want to be asleep during second period. That's Aristotle. A ball rolling down an incline will roll to nearly its original height. Let's see, who was doing experiments? Galileo. All right, what is your weight on the moon compared to the Earth? Well, since the gravity on the moon is less than the gravity on the Earth, although your mass stays the same, your weight will be less. What's your mass on the moon compared to the mass of the Earth? Well, mass is mass. It's a measure of your inertia, and it'll be the same. A 1 Newton force acts in the same direction as a 4 Newton force. What's the net force? Well, it's going to be 5 newtons. A 1 Newton force acts in the opposite direction of a 4 Newton force. What's the net force? It's going to be 4 minus 1, or 3. What does not cause friction? Let's see. Rough surfaces. Well, we know rough is a key word in physics for friction. Microscopic bumps. Actually, this is true. Electrostatic forces. Yep, those cause friction too. So the correct answer here is all of them. Now let's look at the formula F equals ma. Mass and force are directly across the equal sign, so they're directly proportional. Mass and acceleration are on the same side of the equal sign, so if mass goes up, acceleration has to go down for the force to stay the same. So these are inversely proportional. Mass and acceleration and force are directly across the equal sign, so they are directly proportional. Friction. Which of these could be true? It makes a car move forward. We saw that. It opposes motion. Well, that's true too. And it's a force between surfaces that are sliding. Another one. So the correct answer for this one would be all three. What's terminal velocity? Remember the skydiver who jumped out of the plane? Well, it's the velocity where the air resistance equals the force of gravity. It's also the velocity where the object has zero acceleration. Now, true, if you hit the ground at terminal velocity, you're not going to make it. What is your net acceleration? Let's put an is in there. What is your net acceleration at terminal velocity? By terminal velocity, we know that means no acceleration, so it's 0. I have 1 Newton of potatoes. I could feed the most people if I have a Newton, that means I have a weight of 1 Newton. Let's see, so this is equal to mg. So I want the largest mass. The largest mass will occur when I have the smallest gravity. And the smallest gravity occurs on the moon. Which of the following has less mass? 1 kilogram of... They all have the same mass. This is a trick question. Alright, weights are the same since G is the same. Oh, I drop a 1 kilogram block and a 2 kilogram block at the same time. How do the weights compare? Okay, Fg equals mg. So, the weight of the 1 kilogram block is 1 times 9.8, or 9.8 newtons. The weight of the 2 kilogram block is 2 times 9.8, or 19.8 newtons. So that would be the weight of the 2 kilogram block is twice the weight of the 1 kilogram block. I drop a 1 kilogram block and a 2 kilogram block at the same time. How do their accelerations compare? Alright, this is a free fall question. This is trick. The accelerations are equal, and we know the acceleration is negative 9.8 meters per second squared. What words should you look for to see if a problem has zero acceleration? Now remember, physics is a foreign language. I'm teaching how to read the language. Let's see. Balanced forces. That's definitely one. That means the forces going to the left equal the forces going to the right. Think of the student who is being pulled to the left and to the right by the same force. They weren't going anywhere. Constant velocity. Well, if v is a constant, that means a is 0. At rest, well, clearly if it's at rest, the acceleration is 0. Net force, no, not net force. Usually when we're talking about net force, we're talking about applying a force, so there will be some acceleration. So, the answers would be 1, 2, or 3. I throw a football in the air. What does a free body diagram look like at the top? It's a projectile. The projectile always has a free body diagram with just FG pulling it down. Throw a football in the air. What is the net force at the top? Guys, it's equal to mg. Or you could say it's the weight of the football, so either 1 or 2. Don't tell me it's 0. Alright, what is the action-reaction pair to my pushing an oar against water? Remember the rule? Switch the words. So it's got to be the force of the water on the oar. What is the action-reaction pair to your weight? Now remember, your weight is the force of the earth on you. Switch the words. So it's got to be the force of you on the earth. Now remember Newton's 3 laws. Mathematically, the first law is F net is 0, but we refer to it as the law of inertia. The second law is the net force law, or F net equals ma, or we sometimes say force equals ma. The third law is the action-reaction, and mathematically it's F12 is minus F21. Remember that while this is the second law, the first law is a special case. It's a special case for when A equals 0, then the sum of the forces is equal to 0. Action-reaction pairs. Do the forces act on the same object or different objects? Remember, it's always different objects. So it would be the force of the cat on the floor and the force of the floor on the cat. You'll always have two objects and you switch them. What's friction? Remember, friction is the contact force that opposes motion, and it always opposes the direction of travel. So if your velocity is to the right, friction's to the left. Make sure you know the units. Mass is always measured in kilograms. Acceleration is always measured in meters per second squared. Mu, trick question, no units, don't give them to me. G is an acceleration, and we measure that in meters per second squared. Formulas, Fg equals mg. Be able to use this formula to find the weight of an object. Weight or mass. If I give you the mass, you'll have to find the weight. If I give you the weight, you have to find the mass. F net, from our second law, this is always the sum of the forces. This is always the arrows on your free body diagram. And friction is mu Fn. If I have Fs, this is static, which is not moving. Or we're about to get it started. A lot of times we use the word start. It means it's not moving yet. Fk is kinetic. And kinetic means it is moving or sliding. M-O-V-I-N-G. Can't spell today. Unbalanced forces cause accelerations. Accelerations result from unbalanced forces. So, F equals ma. Forces and accelerations are directly related. If v is constant, a is constant. It's a constant, of course, and that constant is 0, and therefore the net force is 0. If a is constant, v is changing. All right? And the force is constant. If F is constant, A is constant. Now, do V and A have to be in the same direction? No, of course not. Think of someone sliding to a stop. Now, which one of these could be a ball falling, experiencing air resistance? It's falling, so we're certainly not going to be accelerating to the right. Of course, it's the middle one. Now, dragging a box to the right with friction. Okay, so this one's accelerating down. Let's see, we need to make sure we have a normal force, and we're going to have friction. Well, if we're moving the box to the right, if the velocity of the box is to the right, friction has to be going to the left. So it's this way. Now, which one of these could be you pushing against a wall to the right with friction? Well, let's see. You're pushing against a wall to the right. So if you're pushing to the right, friction has to be to the left. Now, what is Newton's second law in X? In X, we have no forces. So the force is 0. We didn't really do a lot of these, so I wouldn't worry too much about these. What is Newton's second law in X here? Let's see. F is positive, so it could be one of these. And we're going to subtract off Fk. Let's see, I'm subtracting off K, so I know it's not E. Now you see how F is much longer than Fk? So I know it can't be equal to 0. Mg is not in this one at all. Mg is not in this one at all. So we're left with A. We're going to be left with some sort of acceleration to the right, because this force is much longer than friction. Alright, Mrs. Jensen pushes her magic broomstick away, and she recoils at 1 meters per second. What's the acceleration of the broomstick? Now, this is an action-reaction problem. Let's get the picture here. Here's Mrs. Jensen. Here's her hat. There we go. And here's the broomstick. Okay. So Mrs. Jensen is pushing the broomstick is pushing back. This is an action-reaction pair. The force of Mrs. Jensen on the broomstick is equal and opposite to the force of the broomstick on Mrs. Jensen. Now, Mrs. Jensen recoils at 1 meter per second squared. So the acceleration of Mrs. Jensen is 1 meter per second squared. Now, Mrs. Jensen's mass is 52 kilograms, and the broomstick has a mass of 3 kilograms. Action-reaction pair, we're not going to worry about the negative sign, tells us the force of Mrs. Jensen on the broomstick is equal to the mass of Mrs. Jensen times the acceleration of Mrs. Jensen. This has to equal the mass of the broomstick times the acceleration of the broomstick. Now we're solving for the acceleration of the broomstick. So I want, let me change colors, I want the acceleration of the broomstick. So I need to divide both sides by the mass of the broomstick. So the acceleration of the broomstick is going to be the mass of Mrs. Jensen times the acceleration of Mrs. Jensen divided by the mass of the broomstick. Now we plug in our numbers. Mrs. Jensen has a mass of 52 kilograms. She has an acceleration of 1 meter per second squared. Now you would have written out your givens so you don't have to go hunting for them. And divide it by the mass of the broomstick, which is 3. So the broomstick will have an acceleration of 3 goes into 5 once. 17.3 meters per second. So, action-reaction pair, the forces are equal, so we get an acceleration that's quite a bit larger than Mrs. Jensen's. Now, quite angry, Mrs. Jensen swings her magic wand to stop the magic broomstick. If the broomstick has an initial velocity of 30 and it takes 0.1 to stop, 0.1 seconds to stop, what magic force did the magic wand exert? Remember, the mass of the broomstick is 3 kilograms. Okay, so let me write out my givens on this one. V naught is 30 meters per second. V final is 0 because it stops. Time is 0.1 second. I need to find acceleration. Remember, V final is V naught plus AT. So let me solve this for acceleration. I'm going to subtract V naught from both sides. So AT is equal to V final minus V naught. I'm still looking for acceleration, so I divide through by T. So my acceleration is V final minus V naught divided by T. So let's do this calculation real quick. This is 0 minus 30 divided by, can't read my writing, time is 0.1. So the acceleration is negative 300 meters per second squared. So what was the magic force? F equals ma. Okay, the broomstick had a mass of 3 kilograms. You have an acceleration of 300 meters per second squared. 900 Newton force. Wow, she was mad. Now, we're back to some more of these diagrams. What would be the normal force? If I'm pulling up, we didn't do too many of these. We have Fg going down and Fn going up. Now, because there's a normal force, we know it hasn't moved off the surface yet. So, F net equals 0. What forces do I have going up? I have F. I have Fn. And I have Fg going down, so I'll be subtracting Fg or Mg. Okay, and that equals 0, so our answer is E. Now, what's Newton's second law and why? I'm lifting it up. Oh, let's see. I have Fg going down. Tell you what, I'm not real sure. If it's sitting on the surface, Newton's second law, well, if it's Newton's second law, that means it's accelerating. It means you've got some sort of acceleration. So it has to be C. Now let's review the problems. Suppose I want to draw a free body diagram for a pool ball rolling to the right at constant velocity. Okay. We always have Fg going down and Fn going up. We have a normal force because there's contact. Constant velocity. Remember what constant velocity means? It means acceleration 0, which means you write A equals 0. Draw a free body diagram for a car moving to the right and accelerating. Okay, Fg goes down, cars are always sitting on the ground, so there's an Fn, and it's moving to the right and it's accelerating. So I'm going to draw in my acceleration. I've got to have some sort of force. Don't try to draw in friction. I mean, you could. There could be a frictional force. But, as we know, friction actually goes backward, or goes in the direction of motion. So just draw it like this. Alright, what does Tom Cruise look like as he slides across the floor in his socks? Okay, here's Tom Cruise. Okay, just kidding. Draw a box. Fg goes down. Fn goes up. Now he's sliding across the floor. Let's say his velocity is to the right. Remember, his hands were in the air. All he had acting on him was friction, and it was going back the other way. So his acceleration is to the left, even though his velocity is to the right. Remember, he was slowing down. Now, what do I do about a monkey? Okay, I'm not even going to try and draw a monkey. He's hanging motionless from a tree. Motionless. Acceleration is 0. By one arm. Alright. Monkey has mass, so he has a weight. And let's just call this attention. And it's attention because he's a monkey hanging from a tree by his arm. So, this is all we have for his free body diagram. What is his net force? Well, acceleration is 0, so his net force must equal 0. Draw the free body diagram for a 20 Newton monkey sliding at a constant velocity down a tree trunk. Well, here's the monkey. And Fg is 20 newtons. Velocity is constant, which means he has friction going back up. And his acceleration is 0. Circle that. What is his net force? His acceleration is 0, so his net force is 0. And what is the force of friction? Well, let me do this in red. I want you to be clear on this. F net is 0. So the force of friction points up. So that's positive. Fg points down. Must equal 0. I want friction by itself, so I'm going to add Fg to both sides. So friction has to equal the weight, which in this case is 20 newtons. Okay? And yes, you have to show me all these steps. They're each worth a point. 1, 2, 3, 4, 5. So this is 5 points, just getting to this answer. Draw a free body diagram for a 20 Newton monkey sliding down a tree trunk with 5 newtons of friction. Okay, here's the monkey, and he still has a weight of 20 newtons. And he has 5 newtons of friction, so this should be much shorter. It's not, but it should be. FFR is 5 newtons. Let's see. The forces aren't balanced, so I know I'm going to have an acceleration, and that's going to go down. What is his net force? Well, let me switch colors here. F net equals, let's see, what's going up? I have friction going up, so it's plus 5. And I have Fg going down, so it's minus 20. So friction is negative 15 newtons. Now you know what? You were going to put in the step, because you want all the points, of friction minus Fg. You're going to give me the symbols first. So the net force is negative 15 newtons, which means the monkey is accelerating downward. What is the acceleration if the monkey has a mass of 3 kilograms? Well, F net is ma. I'm looking for acceleration, so I'm going to divide both sides through by m. It goes away. So the acceleration is F net divided by m. F net I found over here is negative 15 newtons divided by his mass of 3 kilograms. So the acceleration is negative 5 meters per second squared. Okay, that negative 5 means he's sliding downwards. His acceleration is downwards. Alright, okay, Miss Jensen's riding to work again. She's just having a day. And she has a mass of 52 kilograms. Let's go on and write out some givens. Okay, there's a mass. And the broomstick has a mass of 3 kilograms. So that's M1, M2. And she's slowing down to a stop with an applied force of 35 newtons. Let's find her, acceleration. The mass of her and the mass total is going to be the mass of her plus the mass of the broomstick. So this is 52 plus 3, don't need that, which is 55 kilograms. Let's look for the acceleration. F equals ma. So to find the acceleration, I need to divide through by mass. So the acceleration is going to be the net force divided by the mass. Now I plug in my numbers. The net force is 35 divided by the mass, which is a total of 55. So I get an acceleration of 0.636 meters per second squared. Now, Mrs. Jensen and her broomstick are in freeze fall. If she has 330 newtons of air resistance, what's her acceleration? Let's draw a free body diagram of this one. We have Fg going down, and then we have friction. This friction is 330 newtons. Alright, so what's her acceleration now? Well, there are several ways we can do this. First, let's calculate the weight. Fg equals mg. Now the mass is 55, and the force of friction is 330. So make sure you write out your givens. So the weight of Mrs. Jensen and her broomstick is 55 times 9.8. So I get a weight, 55 times 9.8, of 539 newtons. Now let's look at F net. Let me find F net first. F net, I'm going to go to my box and look at my arrows, my free body diagrams. I have friction going up, and I'm going to subtract from that Fg. Now, friction is 330 newtons, and I'm going to subtract 539 newtons. So I get a net force of minus 209 newtons. Now all that minus sign means is it's going down. I'm still looking for acceleration. I know F net equals ma. So to get acceleration, I divide both sides through by a. Let's not do that. That would be if I was solving for mass. Alright, let's switch colors. I want the acceleration, so I want to get rid of mass. So the acceleration is F net divided by the mass. F net is negative 209 divided by the mass, which is 55. So I get an acceleration of negative 209 divided by 55, or 3.8 meters per second squared, which is less than gravity.